Thank you, Jason. As Jason said, we met in Hong Kong, and as far as I'm concerned, I'm amazed by the crowd today. Thank you guys for coming out today. And this presentation, you guys didn't get to see the first part. It's on YouTube if you so chose to watch it, but the big difference between this presentation and that one is this one comes, 2 or 3 years after. So I want to show you guys some of the work that we did on Morpheus Tower, the project that he alluded to, the one that we spent 2 hours lecturing on between us, Zaha, and Front. Because I still think that message is something that is still futuristic, innovative in our industry. But I want to tell it with a very special spin. Where has that project led us in the last 3 years? One thing that you guys need to know is technology is an exponentially changing thing. So it changes in 3 years' time the amount of time that it would used to take 9 years linearly. So we have seen a lot of development, and I think that it won't just be that I'm sharing with you guys changes that are happening in structural engineering, because it's bigger than that. It is the way that we work together as architects, engineers, constructors of the built environment to deliver these projects. A little bit about myself. A little bit about myself. My name is Emidio Piermarini. I'm an associate structural engineer at BHoM Engineering in Hong Kong. I've been there for about 4 years. I used to actually live in the Emirates. I was in Dubai for about 7 months to start my career out there. Just began with BHoM Engineering. And my career timeline is I was not too long ago, I was in your seat. So I started my career in the United States. I graduated from MIT and I came straight out to BHoM in Dubai. And one of the things that I can recommend to all of you is if you want to do awesome projects, you need to be flexible and you need to know how to use the machine. You need to have good first principles architecture, but you also need to be able to interact with other people and the computer, treating the computer just as equally as a design partner as the other people around you. Communication is key. I've been really blessed to work in all of these different projects in a very short period of time, mostly because of those traits. Now, all these projects, these are some of my favorite ones, some screenshots from my favorite ones. The main thing that I want to go over today is 3 things. One is a case study for Morpheus Tower. We're going to go over that. 2 is the history of data in the AEC industry, architecture, engineering, and constructing. Because to be able to tell you where we're going next in relationship to Morpheus, we have to set that scene. And then to end, I want to introduce to you guys the world's first open source language for us to communicate, not only around the sketchpad, but in the machine. A truly open source approach to what we do for a living. Okay? Disclaimer. Nothing that I'm going to say today beats this rule. What you're learning right now are first principles, what it means to be an architect. Like I learned what it means to be an engineer, the actual bread and butter of what it means to do your craft. You need to know that. There's nothing that's ever going to replace that, and don't let anybody tell you that they're going to have a button that will replace you on that. It can't happen. It will never happen for creative, heuristic, beautiful tasks. You will always be better than the machine when it comes to that. I always start because there's a lot of people who sometimes get confused and they think that because we're talking about the machine, we're talking about doing only that. It's really dangerous when people do that. So please do not get me mistaken. First principles, what you're learning right now, is something that you need to have. We take it as a given. You need to be a good architect. But to make yourself an even better architect, that's where the machine comes in. It can be a really useful tool. In this case study, you can't make buildings like this without both sides of it. You can't be just a good architect and make that. You need to actually make it in real life. You need to have good computational skills, you have to have good communication skills, you have to be flexible, you have to work hard. This particular project is one of my favorite. I was on it for 4 years, so the majority of my career was spent on this particular project. And when you look at it, it's in Macau, so if anybody's ever been to Macau, this is where the famous Cotai Strip is right here. So this orange line. So that's basically like Las Vegas. So this is a hotel casino, and as such, they can afford Zaha Hadid to come in there and make something that is from its very genesis, was meant to be a landmark structure. So everybody was on their top of their game when it came to this building because they knew we are here to make a cultural icon for the city of Macau. If you've ever been to Macau, they don't have much of anything when it comes to good architecture. They have a big pineapple building, and that's about it. Pretty fair statement. Yeah. So usually, 3 years ago, me and Jason, all we had were these, and these, and these renderings from Zaha. So blessed to say now, 3 years later, I can share with you guys videos of the actual building, starting with the reveal of the 7-story tall atrium. So this is, if you look at this, this is the first hole of the exoskeleton. So you're looking up from in the 7 stories. This is 7 stories up right here. You're looking up. I'm going to show you what happened at the opening ceremony when they did the big reveal.
Distinguished guests, on my mark, 3, 2, 1.
Everybody's phones come out.
3, 2, 1.
Now, none of us knew this was going to happen. And to this day, after working on it for 4 years and being there in that moment, I really hope for all of you in your careers that you feel even the way I feel right now when I watch this video again. Because it was amazing. It was so amazing. And it wouldn't be Las Vegas without a bit of showmanship. That was a really good night. And this is a video from the scenic lifts. Sorry, I think I'm getting a bit of feedback loop here. So this is the video from scenic lifts, 42 stories tall, this building. And as you can see, all the way up and down, that beautiful exoskeleton, the world's first free-form exoskeleton, completely on display there. Now, everywhere where one of that crazy spider web comes together, all those little junctions of all those members, that was my realm. That was the specialist realm that really required structural engineering and computation to come together. This is the 7-story atrium on a not orchestral day. Pretty cool. So again, it's 160 meters tall. It's mostly hotel space, but there is some very VIP gaming facilities. If you want to stay there, I think it costs something like 5,000 dirhams a night. So most of us who designed it will never stay in it. But, you know, one can dream. Now, the structure is something that we get into real quick here. So we have 2 cores. We have 2, so you guys saw those. I just went up and down one of them. We have a steel exoskeleton, and both of them together help hold the building up, not under just gravity loads, but also under seismic and wind loads. Remember, it's a typhoon climate, so it's not like wind loads are small. It's very big. And what that means architecturally is all of that space on the inside is completely open. Right? So that exoskeleton is working structurally, so it's carrying severe loads. So engineering-wise, this was a big challenge. Equally for our facades colleagues, they had a lot of other things to consider as well. So I'm not a facades guy, so I'll leave. Next time we'll go into more detail on this. But the exoskeleton is offset from the edge beam, so it's outside of the facade line. Now this causes certain complexity right off the bat for the engineers. But one of the main things we have to understand is when you see something like this, you have to understand, if you don't understand geometry from first principles, nothing annoys me more than people who don't understand geometry just because they can create this in the machine. That people who don't understand a triangle has 3 points. It might sound weird, but literally I've had that before because people get in their head that, oh, the machine, it knows what it's doing. It's ridiculous. So one of the first things that we had to decide was managing complexity. It's already a hard project. Let's not shoot ourselves in the foot and make it more difficult. So one of the things we had to decide was that envelope that you just saw from Zaha is weird, wonderful, warped, three-dimensional, and 2D curvature. So we have a decision to make as designers. First big decision that the machine's not going to help us with, because this is what we're about. do we have some prismatic member, something that is able to be warped and, strictly speaking, follows the architecture? So the steel member, remember, something that carries the load of the building, follows that. What that would allow for is the facade people to just have standard brackets that are always one length, right? And they go out to the aluminum clad panels, right? Do we do that? Or do we do something like this, where all of the members are planar? They have single curvature. And by definition, what that means is that when all of these members come together right here, like shown right here, it's just a mishmash of steel. Nothing, by definition, will line up. Now, we decided early on, good engineering principles says, you guys see this right here? Do you see how many people it's taking just to sort of jig up a member? That is not where the complexity needs to be. That's a very difficult thing to handle, to do that for the tens of thousands of members that we have in the exoskeleton. What is pretty easy is to have facade brackets that can modulate along a member. So we said, okay, great, we'll keep the complexity in the facade brackets, but there's no free lunch in this world. That means that we have to deal with that. We've pushed the complexity all the way down the road. We kicked the can down the road, but now it's time to deal with the big boy stuff. This is really where the rubber hits the road. Now, in our industry, we have things that we need to do, and we have tools. Now, all of these tools do different things, but meanwhile, we still have to do all of this stuff, right? So we don't have a common consensus. Remember that. We do not have a common one perfect tool to help us with big tasks. So that's the realm of someone like myself, some sort of person who can sit there and fill in the gaps of the industry when it comes time for the things that actually, okay, great, we made these very important decisions, human decisions around a sketch pad. How do we actually now create a building which has millions and billions of moving parts? And I say moving because when you're in design, there's never pens down. I want to let you guys know that. Not to give you guys a license as the architect to always change things. There should be pens down on some things at some point. But the underlying trend that I see in the industry is you can change anything you want, anytime you want, even after the concrete's poured. Just keep changing it. Why not? We have the machine. It can help us. It's not right, but it's what we're meant to deal with. That comes from the client sometimes. That comes from the architect. It's stuff that is happening. And these tools are not made for that. These tools are made for Reba stage 1 is over, pens down on that. No. We have lots of stakeholders and lots of complexity in a modern job beyond just complex geometry. Remember I said, pushing something down the road. This is that mess, a mishmash of steel coming together. This is another example of mess, mishmash of steel coming together. Yet another one. There is no book to solve this problem, especially multiple times. There is no software to solve this problem. There is only good engineering principles and trying to apply that on a massive scale like never done before. The concept of what we had to do, there were 4 main challenges. Each of them on their own would have been a project in and of itself. To do this, to deliver 2,500 connections, fully detailed in 12 months, is something that's never been done on that size and scale. So we had to innovate right off the bat. And what we did was we said, listen, we need to fill that gap. We need tools that are empathetic with our task, not the off-the-shelf tools that everybody gets for, because, oh, hey, one-size-fits-all solution to your problem. No, we don't have a typical problem, and we have to take responsibility for what we're doing here. So the 5 typical steps that we'd have to take is, 1, 2,500 connections. You have to try and figure out where the similar ones are. And that's not so straightforward on a building like this. Because if you can do that, you can start dividing your work by a factor of 2, 3, 4, 5, 6, right? So you need to figure out how to do that. The second one is you need to use your engineering mind and your 3-dimensional skills to actually understand, what does this thing look like? How can we mold something that not only works for engineering constraints, but also for architectural constraints? We'll get into that in a bit, why that's difficult, particularly for this job. At the map courses, which is something that we won't go into today, I could do a lecture just on the engineering, which is step 3 and 4 here. But I know my audience, and I know that might put everybody to sleep. Very cool engineering on this project. Analyze the connection again, talk all day, and documentation of the connection, which in this project was done mostly in 3D, not on 2D drawings, which is pretty innovative in and of itself. So step one, find similar connections. So if I told you that there are certain criteria for what a connection needs to be. So when all these members come together, again, look at the sizes of some of these bad boys. 500 by 500, there should be a 700 by 700. These are big members. Me and you, we can crawl around in the inside of these big members. How do you actually know what the criteria is for where they all come together? Can we have one detail? Well, you can actually come up with that on paper. What's hard is to actually figure out where that happens, because it's not so readily apparent with the tools that we have, right? So you can imagine if my hand is the connections to my fingers, right? These actually work pretty well so long as the angles between my fingers are the exact same. But the second that my thumb's profile comes to my pinky and this one stays the same, it's not the same anymore. So there's multiple criteria. So we had to make tools with the big grasshopper script that you're going to get to see a lot today to actually help us get to the point of dividing our work by a factor of 2, 3, 4. In the end, we had about 450 unique connections out of the 2,500. Now, the next part's the cool part. Concept design is, to me, the part of the project everybody wants to work on. It's where there's low amounts of stuff that you have to produce. It's very low pressure and creative. Detailed design is where it starts to get, the pressure starts to be turned up. There's a lot of stuff to do. And it's like, after this, it's over. So, you know, you're the last one holding the bag. So it's really cool to work on a project where you get to do concept design every day, because there's a new concept literally every 4 hours right around the bed. Not to say that there wasn't pressure, because you have to be able to bounce this out. This part of your job has to be automatic. The first principles of good connections, engineering 101, has to be automatic. Going back to my rule before, you don't get to just say, oh, the machine generated all that. The machine helped you visualize it. He didn't come up with that sketch, and he definitely doesn't understand what's going on other than just, hey, here's a picture for you. And you guys can kind of see the size and scale of these connections right now. That's just the connection, right? That little guy over there, that's just the connection. And we had to do this for all of the connections. It's really cool. And as part of that, you're using your engineering logic, but also you're sitting here and you're saying, Zaha's given us this crazy freeform warping envelope. If you stick out of that by this much, remember, you still size those connections. I've gotten emails that said, hey, you're out by like 0.01 millimeters. I'm like, so what? Like, who cares? Don't worry about it. Just get it inside, right? So you gotta be accurate. You have to know what you're doing. And you have to be able to work in awkward positions like this. So the ability to work in 3D is, to me, paramount for our industry. It's another pet peeve of mine is when people can't work and think in 3 dimensions. We need to be able to do that. We create 3-dimensional things. The epitome of being able to work in 3D flexibly and adeptly is to be able to use Grasshopper to actually sit there and make it a video game, to make this envelope really a non-issue. We can actually sit there, and just as if it were something that you were playing on your phone, get this connection to not clash with the envelope, which is what you're seeing here right now in live time. We were able to sit there and say, what's a good connection design, A, and B, how can we script it so that we know there will not be clashes? So in a matter of minutes, a good engineer can take a good concept and make it feasible for every one of the 2,500 locations that it needs to exist. Those were the time scales that we had to work to. Then, like I said, we get to be cool nerds. We get to go and say, great, left here, we know what we're doing. Good connection design, works with the architecture. Now how do we justify it? And I could get into it all day, but we won't. It's very difficult to do that type of analysis on the right. We need to be able to do it. It's necessitated by the complexity of the geometry, the complexity of the forces. Let's leave it at that. But it deals with some stuff that most structural engineers never, ever, ever have to deal with. All of these things and big data. It's a really, really cool task. And to do that brings me to a principle that I want you guys to remember about computation in our industry. There's something really powerful about not just designing a thing, but designing the thing that creates the thing. That makes sense? It sounds weird. You'll see what I mean. If you can create the thing that makes the thing, you are in control, bigly, all right? This is what it's about. You have to be able to do this, because this is really, really, really powerful. This allows you to do things like this. You don't have to wait for Autodesk to sit there and say, oh, hey, when am I going to be able to map my forces? Oh, no, I can actually just do it myself. I can take control of my design and actually do what I want to do. So what you're seeing on the screen right now is we had to do all these connection analyses. And there is no one tool that will allow us to see this very important metric right here. So we scripted it. And as part of that, as being able to say, we own this design so much, we were able to build in all these checks, all these visualizations that made it such that under no circumstance is the engineer not in control. That the absolute care of the engineer, the extension of his hand, is put at the forefront before we do anything out the door. Anything that happens must be in our control. Again, going back to what I said before, it's all about first principles. Everything that you're seeing here is about first principles. Again, this part of the engineering, I did keep this in there. The most important part is that in what we're dealing with, if you pull something in 4 directions and they're all going outwards, that gives you something on the right. But if you change 2 going one way and 1 going the other, you get red. I think we all are familiar with the concept of red is bad, green is good, that type of thing, right? So that's where we'll leave it for the engineering right now. We don't want situations like on the left. That causes our building to fall down. So we need to use a model such as this to go over it. And that's how many we had to create. I can't stress this enough. I love this graphic because any one of these little Brady Bunch cubes here could have taken a normal engineer, quote unquote, without special tools, a day or 2. We had to crank out, this had to be done, I don't know, in maybe 2 hours, every day for 9 months. You didn't have the luxury of, oh, I can take all day to just do the analysis. You need to get it done, son. It needs to be done yesterday. You need to document it. Good engineering practice to document it. Pretty colors. I'm a big fan of pretty colors. So that's what we did a lot of. A lot of documentation in 2D, because that is something you can't, in 3D, it's very difficult to get across every idea. So you need to be able to do both. But we did do a lot of 3D documentation. So if you look right here, this is a typical deliverable that we would give to the contractor. All Rhino files, giving it over and telling them, here you go. And you will see here very soon, that made it seamless to actually transition from digital to reality. Right? So this is one of my favorite. Don't need the music for that one. So this is an experiment that I did after the project was over. Okay? Now this is, to me, the epitome of liking your job. You go in and you'll do something over the weekend. You'll take your phone and you'll clamp it up above your doing hand calculations that no one cares about, no one will ever see, because you're redesigning something that's already been done, and you know that the way you're doing it is incorrect, basically. But you're trying to prove a point. I hope you guys can all find that in your careers when you go forward. Because this, when I made this, I didn't expect to get the results out that I did. So what I wanted to do is I wanted to go back. We were forced to innovate. We had to do what's on the bottom here. So we said, well, what would have happened if you went the other way? What could have happened? So you could do these kind of connections by hand. You can. You have to take a lot of conservative assumptions, but you could do it. And what you're seeing on the top there is me doing just that. And there's a timer there, if you see my iPod. That time scale is the same as the bottom, right? So what you're seeing here is actually, right now I'm about 3/4 of the way done with the analysis at the bottom, whereas at the top, I'm just getting started, right? Most of my time up at the top is being used by copying and pasting things from the screen down to my notepad and doing calculations very, very slowly and conservatively. So we obviously knew when you use technology, there is a time benefit, but we didn't know how much. We didn't know actually how to say, well, Mr. Client, we're saving you 20 months, 10 months, 20 minutes. So this particular exercise showed us 2 main things. One, it showed us that it was about 20 times faster to use the computational approach than to use the hand methodology, right? But the other thing that was shocking was it also showed us how to actually quantify the material savings, the savings to our environment, which was a factor of about 3 times the materials that you would need from using the computational methodology to the one that would have happened before. So it's not to say that we did anything that couldn't have been done before. It's just the issue of, I'm trying to fast forward it to the point where you can see that. Because at the bottom, we already produced a 3D model down here. There's up at the top here. Up at the top here, I think I'm only 1/20th of the way through. That's how we came to the final number on the material savings. There we go. So my final number was 140 millimeters. 140 millimeter plate that was needed for one of the plates. That's a big plate, just for the record. If you ever see someone using a 140 millimeter plate, it's wrong. That's a pretty good rule of thumb. And that's visualized right there. So the purple one is the one that we made doing it the right way, the computational way. And the other one is the copious amount of conservatism that you would have. And that's just for some of it, right? So if we actually did this full on, all the way through, I took the 20 times longer than it took, what you'd find is that box right there, what we'd do is we'd just cast it full of steel. There would be no air involved inside. It would just be straight up material. Now, the cool thing about this is you're taking a fly-through right down the center of the building. This is what we delivered to the contractor. And the statistic on top is a very important one. Because when you communicate digitally, we only had, out of all of these connections, 2 RFIs of substance that dealt with things that, if you guys know RFIs, requests for information, right? They ask you, hey, your design, what does this mean? Only 2 times on that most complex part of a very complex project could you actually sit there and say, oh, yeah, sorry, we missed that. Here, let me give you. That's unprecedented. That kind of clarity only comes with delivering that level of detail. And the other cool thing is this, everything you saw there in that fly-through, that was made from this. Me and my boss, over a cup of coffee, sitting there and saying, what would be amazing is if we could, in the most complex part of the complex building, make a detail that was modular, flexible architecturally, great structurally, and makes the contractor happy so that we'll only have 2 RFIs. Going back to what I said at the beginning, there it is right there, folks. The computer is not getting out the butter paper for you and writing on all of these brilliant ideas. That's you. To get it into the machine is also you, and we'll come to that very, very soon. It's not anybody else's responsibility, your design, other than you. So again, this script is very important now because we're about to transition to, this is in the past, this is ancient history in my opinion. But this is still, for most people in the industry, they'll never do this right now. Don't let me fool you to say that other people are doing this. Because in each one of these little blocks, there's either lines of code or there's more of this. So if you look right here, that red box, that's this inside. And by the way, there's more of that in this one. It's like Inception, a dream within a dream within a dream. Tin can, one of my favorite definitions ever. I've since learned how to script a bit cleaner. So, you know, we're all getting better as we get older. And there's some cool images that I really, the first time I ever went to China to go see some of this stuff, to actually see the future. You know, we always hear about China in the news, and you hear about how they're making stuff, and just China to me is so exciting and mind-boggling. I was just jumping around. They were like, hey, calm down, like this is a factory, you're gonna get hurt. But like, you know, to walk around and to see some of these things that look like 2 inches wide on your screen for 4 years, and then actually see a shop yard full of them is really, really cool. So where does that place us on the grand spectrum of time? Okay. So how does that fit into what you guys are doing, what I'm doing? Like where on the spectrum of things does that place itself? How do we contextualize that process in everybody's workflow or everybody's job? I think for us to understand that, I kind of have to contextualize the industry as I was introduced to it 10 years ago now in Northeast Ohio when I had my first job in construction. And I saw this cartoon on the wall. Because the more I'm in our industry, the more I kind of understand this cartoon. Our industry is embarrassingly known for stuff like this. We're famous for delivering projects late, and we're delivering projects over budget. And it's mostly because we do work on hard things. Every building's bespoke. Every building's attacking a new problem. So it's not like there is a manual that we can go and say, hey, how can we do this? But we don't do ourselves any favors either. Construction industry is one of the least digitized industries in the world. And look at our production value over the last century. We went down in production when everybody else was exponentially getting better. We are the worst, other than agriculture and hunting, construction is one of the worst digital industries there is. That's really a problem for everybody in this room. The average age is probably 25 in this room, and we all grew up with computers. So it's really annoying sometimes when basically you're in an industry where it's like, reams and reams and reams of paper. Because you know inherently that's not scalable. You know inherently that something's wrong when everything is literally smudges on a paper. So speaking of that, let's look at something. Let's look at what the history of data is in our industry. Let's understand how we came to where we are right now. It's something you don't normally think of, but it's something that I think of quite often. When I went to Stuttgart recently to go to a conference, they had a really good article. It was Fabricate 2017, and it was an article about how Brunelleschi, the original master builder, was sitting there and was using turnips as part of his drawings, what we would call drawings. He was using quick physical models to show everybody what needed to be made. The thing that made the thing was a turnip. And that's the way we did it for quite some time. The master builder was in control, he knew everything, and he crushed it with turnips. He took responsibility for turnips. Alberti came along and he said, can't be having that, all right? That's not good enough. Let's make some drawings. Let's draw the thing. So the thing before the thing was drawings, right? So for many, many, many years, our industry was nothing but drawings. And we did some really, really cool stuff. More cool stuff than we do today, like Mr. Guastavino cooking up these awesome staircases with nothing but 2D drawings. And I've seen this 2D drawing for this particular staircase. I couldn't find it on the internet. It's one drawing. It's a piece of art. But at the end of the day, I like this quote, and I like this picture. They're only just dirty marks on paper. That's the data. The thing that makes the thing is just this thing that requires you to understand how to read drawings. It understands that you've created the drawings properly and detailed properly. So there are problems with storing your data in that way, but it works. Now this is where we started to, I think, that exponential curve that everybody else took, I think this is where we started to kind of plateau off and go down. Because when the digital age arrived, our first instinct was, instead of sitting like every other industry and saying, how can we take the industry and topsy-turvy it and turn it on its head and shake its pockets loose, we said, the dirty marks on paper, dirty marks in the machine. We can sit there and digitally have a line. And it'll be so much better because now when I have to offset, I don't even know how they did it before, to offset a line and rulers and all that other stuff. I see that you guys are learning that here, which I still think is amazing because it's really important to understand geometry. But that was what we did. We said, hey, we're going straight to the machine. And then comes my least favorite term in the world, BIM. You didn't hear me say that yet today. And if it was any other industry talk, you would have heard BIM as the first thing. BIM, 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 BIM. But not for me, because I understand the holistic idea of what BIM is, which is supposed to be transcendental in our industry. The idea that we are creating the thing as it is in real life. Not just that we're modeling it in 3D, but we're modeling it with all of the attributes that it has. We're making a digital twin of what we actually want in the real world, because just like the turnip, it's easier to make the digital twin than the actual real thing. But where we've gone wrong with this very good idea is we've made it commercial. We haven't taken responsibility for this definition. It's become proprietary. So when I say BIM, most people in the industry don't think of that first definition. They think of a software package. They think of throwing stuff into a proprietary product. Now that's opened up the next stage of things for people like myself who actually said, we understand that those guys could never produce This is what they do. They produce a piece of software that's supposed to appeal to the masses and be a one-size-fits-all solution to everyone's bespoke problems. It's impossible. It is impossible. The definition of insanity is to say, I can create one tool that will solve every problem for every single bespoke situation in design. And that's why you see the realm of these people like myself and others coming up because they realize we have to patch up. Even the software companies have given us these interfaces because they've said, we can't solve your problems, so we need you to solve them for us. They're the ones collecting the checks from us, and even they were like, we're done helping you out, like you sort it out from here. So this script right here is at the very end of that long journey in terms of data in our industry. This is as far as you can take that ninja approach, the guy who just sort of mashes together spaghettis and batteries to get those softwares to work together. That's it. And that brings us to the very important point of the day. What's the future? What comes after that? This is the one I think for everybody in this room is really, for students in this room, are very important. This is about skills, not scripts. This is about skills, not the scripts. I can give you that script. I can give any engineer in the world that script. They won't be able to use it. Because to use that script, not only do you have to have great first principle engineering, but you actually have to know good first principles computational skills. You actually have to understand holistically what's going on. That thing is just an extension of my hand. And it's because I created it. And the only person who could have created it was the person with the problem. This is strictly speaking about skills that you need in your life. We're speaking English right now. A lot of business is done in English. It's a skill that you need if you want to be at certain tables. What I'm here today to tell you is these skills are things that you will most likely need in your life. Coding is something that is going to be expected of all of us very, very soon, if not already. And the way I think of things is like this. I think of the hierarchy of what skills are most important. So for me as an engineer, math and physics. If you don't know math and physics, you're not a very good engineer. If you don't know engineering theory, you're not a very good engineer. If you don't have any practice, you can have both those right out of college, but you're not a good engineer yet. You need practice experience to be a good engineer. You know something about building codes and software. Same thing goes for architecture. I just don't know what they are. Shape grammars, architectural precedent studies, all that other stuff, right? But that's what you're here to learn right now, the base knowledge that makes you an architect. Because if you were just, and somewhere in between all that is what I call computational engineering. But if you were just that person who knew how to use CAD, who knew how to use building codes, we wouldn't call you an engineer. And I don't think we'd call you an architect if all you knew how to use was CAD. We'd probably call you a draftsman, right? So your power goes up, very much so, the more wide of a base of this pyramid that you have. The more knowledge that you have at the base, the stronger you are. Same thing goes for computational knowledge, right? Knowing how to code is very important. It gets you more power. But you're a cook if you only know how to code. They call it kiddie scripting in the Silicon Valley world. If you don't actually know the computer science theory and the statistics and the mathematics and actually how the compiler works and all that other stuff, the levels of abstraction from zeros to one all the way to what comes at your fingertips for free from one of these things. If you knew how to take this and go all the way down to zeros and ones, you're that guy up there. Now, in our industry, you see a lot of people only have, let's say, this guy. That's okay, right? It's better than not having, it's better than only having this stuff. That makes you an engineer. A lot of companies want to just say, great, we need some of that computation. Our engineers are precious, they don't know how to code, so we'll buy them a computer scientist to sit next to them, and they'll work together. That's better, but it's not nearly as good as that guy up there, who took it on himself to actually sit there and say, I'm going to learn both pyramids. I'm going to learn enough about that side of the coin to where I can actually start to stack my pyramids, and I'm going to end up all the way up there. And this graph, I made it this morning. I've been working on it for a while. This is an exponential graph because, like I said, technology is exponential. And I can tell you, BHoM, we don't work in that way. but I've seen other people work that way. And you can imagine the communication lines, and it slows things down to actually have to explain to someone else what a beam is or what a mullion is. When you actually know the one pyramid very well, and you augment it with the second one, again, first principles, architecture, engineering coming first, augmenting that with computational knowledge, ninja. And that's mostly because you will start to understand where the complexity is best kept. So, as a computational engineer, I can say, when it comes to these kind of tasks on the right over there, or left for you guys, those are the things that a human being should be spending their time on. Human mind is a terrible thing to waste on A plus B equals C tasks. If you have to copy and paste stuff between spreadsheets all day long, you're doing something wrong. Your brain is more useful than that. It can be done with a machine way, way better. Don't waste your time doing that. And that brings us to the BHoM. The buildings, see, I always know the original title of the BHoM, so we've changed it so that it wasn't Bureau-Happold Object Model, so I always have to look at the slides for this one to actually understand. Buildings and Habitats Object Model, that's what it's called, and we're sticking to it, is now an open source project, and it's something that we've been working on ever since, like I said, me and Jason had that first conversation about Morpheus Tower. 3 years to actually go out there and say, what is the solution? What have we learned from Morpheus that can be applied everywhere in the industry? What was useful from there that wasn't just useful for us, but was useful for everybody? So we've already gone over the introduction to the data. What is the BHoM? At its very core, the BHoM is a common language for you and me. It's a language that we control in the machine, that we don't have to wait for someone else to fix. When it has a problem, we fix it, so that we can have this common vernacular going forward in the industry. What do I mean by that? I told you you'd see a lot of this script. When you see this script, again, if you double click on node analysis over here, you see node analysis, there is a definition of lattice node. I don't know how many of us know coding, but basically here we're defining something called a node, and it has all of these properties, right? Now what we noticed was all the computational engineers, all the computational designers on their projects, they're all doing this because they're all taking responsibility for the definition of what they're creating digitally. So everybody who's this computational ninja for the past 3 or 4 or 5 years has been working in parallel, but they're all doing inherently the same thing. They're taking responsibility for what they need to create digitally. So we have a lot of different softwares, and it gets to be a mess to actually communicate with each other because we don't have a common language. Wouldn't it be great if we all stopped working in parallel and we worked together to define that common vernacular that we all use? Because at that point, to talk to different softwares, because software isn't about design. Design is not just software. It is not software at all. There's just a means to an end. So if we have a common language, just like we have around the Sketchpad, we can translate it once and be done with it. This is a fundamental shift in the industry when we stop talking about software and we start talking about design, and we leave the translation and interoperability issues for later. This applies to all of us. It's not just structures, it's not just MEP, it's not just facades. So the key about this is it's us. We sit here, we define this. This is something that you can go on the internet right now and download and participate in. It's community created, and it's very much been made with you in mind, because we know you didn't learn, you're not a computer scientist if you're in this industry. You're not someone who knows how to code very well, if at all. So we've lowered the bar. The first thing we said is we need a common language. The second thing we said is people to create that language don't know how to code. So the third thing we said is lower the bar. Make it easy for people to participate. To give you an idea of what I mean by this, everything is defined. We need to own what we're doing. So even something as pedantic as a point. Here you can see circle and a point. No surprises there, and you say, why do we need to actually define something that pedantic? It's because we don't want to have anything that isn't in our control. We're not reliant on CAD to define what a circle is for us. Everything has to be explained from first principles by us, taking responsibility. keep saying that. It's very important. Take responsibility for what it is that you're doing. And then from those little objects, you can start to build up something that's a bit more big. So a BHoM speaker object is an amalgamation of a bunch of other properties and objects. What can you think of that you do, an object that you need, and how would you define that? If you think about it, it's a very interesting conversation when you have to actually define from very, very scratch what it is that you do. That's what we've been doing the last 3 years. So the BHoM is the data defined by us, owned by us. The software is over there. The engine is something that is an algorithm that takes in our data and does stuff with it and gives us out new stuff. And the UI is where you expose yourself to the BHoM. So for instance, you can make a script of the BHoM via all those user interfaces. You guys can't use Chrome yet, but the rest of them are open, right? So you can attach yourself, the BHoM, to Excel, Dynamo, and Grasshopper. And again, how scary is it? All depends on where you're coming from. But when you actually use it, if you're just going to be a user, this is what you see. In all of the media that you're already in, this is the user interface. And there's no surprises here, because at the end of the day, it's something that you've defined. You understand inherently what this is. You're in control. So this allows us to do a couple interesting things. So what you see on the script here is we're creating 3D rhino points up here at the top left. We're converting those into nodes. Those are actually BHoM objects now. And now, because they're BHoM objects, we can push them, pull them, put them anywhere we want in any of the adapters, right? Because we're speaking the same language, it's seamless for us to put it anywhere else. So this is an example of that. Equally, it opens up new possibilities for us to actually sit there and understand our data better. So now we own the definition of the data, and we can actually sit here and use these tools as an extension of our hands. We can actually sit there and say, listen, instead of quibbling over all this different stuff, let's talk about design. Let's understand what it is our building's doing, how it's performing. So this is the future. This is the future that you are going to enter the industry in. So there's 2 rules that I want to suggest to you before we complete today. Rule number 1, I've said it millions of times today, and I'll keep saying it. You have to take responsibility for your design on paper and in the machine. You cannot sit there and blame other people on why you can't portray your design in the machine. You can do this on your own. We are doing it right now. We are proving that you can actually be the guy who goes in there and defines what something is, to take responsibility for when it actually has to go out the door. These guys did it. If you know anything about computer notation, there's a lot of hierarchy being described like this. Brunelleschi.turnip, Alberti.hand.line, right? It's all about the hierarchy, right? You see this a lot in actual computation. Autodesk.designscript.geometry.line. You see that all the time. The problem that we're trying to solve is let's stop worrying about that. And let's start going back to just this stuff. Let's take responsibility again, just like those designers of old did. Let's not wait for those guys to help us out, because those guys aren't going to help. And we have open sourced this code, and we did it in a way that actually allows you to go in as a brand new beginner and do it. And you guys are at university right now. You might be busy. I remember when I was in university, I thought I was busy. You ain't seen nothing yet till you're in the industry. You have a lot of time on your hands, believe you me. Especially architects, like, man. I feel good to be an engineer. Sometimes we get to sleep, but architects I know, like, they work 24/7. So if you think that you're going to be able to go to the industry and get this stuff, you got another thing coming. The industry is not an industry that innovates very often. It's not an industry that invests in its people very often. Invest in yourself now. All of this knowledge is free. Everything that I talked about today is absolutely internet on your phone free. You can do it. And the second big rule is think agnostically. Think agnostically when it comes to this stuff. You're not allowed to come in here and have a bias against against certain softwares or come with bias from the software houses or from your own discipline. This is an open source project. So you guys might not like this, but I always say to the architects, just because you guys are usually up A, E, and then C, doesn't mean that the BHoM is going to be structured that way, to where the architectural objects are at the top of the pecking order. They very well might be, but we're going to have that conversation in the BHoM. We're going to have that, well, really, what is the agnostic definition of a chair, of a podium? Does it really matter about the structure? Does it matter? I don't know. But those are the conversations that we hoped when we open sourced this to spark. So I'd like to thank you for your attention today. That's all I have for you. This is the links to the BHoM. This is something that I really highly recommend you guys at least go take a look at while you're in university, because I do believe wholeheartedly that this is the future of our industry, an open source approach to the objects that we create. And I really think it's a special time for you guys to be coming into the industry because it's so easy to disrupt. We are behind, and it will be very easy for you to be, if you do this stuff and actually think about it, to be a superstar when you come out. So I'd like to take any questions now that you guys might have. Thank you for your attention. Oh, yeah. Can you speak up? So the question was, is it basically an index where you learn how to script? No. So if you go to this website,